about exotic form of perovskite. What is yours?
So I was examining Ruddlesden-Popper perovskites, and so the generic perovskite, you see a generic layer here. It has a ABX3 crystal structure. So what that is the A and the B are cation, and the X is anion. In my case, I'm looking at cesium lead chloride perovskites. So then what the Ruddlesden-Popper perovskite is it, in addition to these ABX3 layers, you have AX layers that offset them. And there's a second type of Ruddlesden-Popper perovskites. It's called hybrid Ruddlesden-Popper, that instead of an AX layer, it uses a layer of organic ligands to separate. So here you have the two models I was looking at. So on the left here, you have the hybrid Ruddlesden-Popper perovskite, and the organic ligands that I was using to separate it was a propyl 1,3-diammonium. And over here you have the Ruddlesden-Popper phase perovskite. And so the perovskites themselves, which are these structures, are cesium lead chloride, but the halide that was used to separate them is a iodine. And you'll notice that if you look at it, the ligands are, the perovskite layers are offset from each other between the top and the bottom. So here we have the density of states and absorption spectra for both of my models. So A and C are the hybrid Ruddlesden-Popper, where B and D are the Ruddlesden-Popper phase perovskite. And they have similar absorption spectra, although the hybrid does show a small peak around 450 nanometers. And here we have the HOMO and LUMO orbitals of my hybrid model. So the blue orbitals are the HOMO, where the red are the LUMO. And this figure off to the side of each is the one-dimensional projection of these orbitals. And you'll notice that in the LUMO, the orbitals are localized on the lead atoms, where they're more spread out in the HOMO. And here is the same model for my Ruddlesden-Popper perovskite. This one, there's localization on the halide atoms for the HOMO, where the LUMO, said that backwards. The LUMO has the localization on the halides, where on the HOMO it's localized on the halides and the cesiums. Not the cesiums, the leads. This is the molecular dynamics of the hybrid Ruddlesden-Popper model. You'll notice that most of the activity appears to be localized to the organic ligands that separate the layers. So in conclusion, we see that these two layers have similar absorption spectra, and to really determine any usefulness as photovoltaics or as a light-emitting material, we would need to determine their non-radiative relaxation rates. We should also need to examine what the effects of additional perovskite layers. Both of the models I was using had 3 perovskite layers before the intermediate layer that offset them. And we also need to use different halides for this process. It has been shown by other groups that halides affect the band gap of these materials.
That's it? Okay, let's thank the... Any questions to the speaker?
Yeah.
Can you go back to your density of states? So I noticed it looks like B is a larger gap.
B does have a larger gap. It was approximately a 2.8 EV gap for the Ruddlesden-Popper phase, where the hybrid had approximately a 2.3 EV gap.
What do you think accounted for that change? So to see the gap go up makes me kind of wonder if it's losing kind of its...
So I know that in these materials, when you use the larger halides, the band gap decreases, but that doesn't make sense for this situation. So the iodine instead of chlorine, or bromine instead of chlorine, for instance, decreases the band gap, but that wouldn't make sense here, as I am not sure what would cause that.
Okay, more questions?
Yeah.
Can you go back to your models? You kind of never explained what your ABX3 meant. You just showed us all these dots and the colors. You never. I didn't know what I was looking at. I was wondering if you could talk about that again.
So right here, trying to outline it. You have the perovskite also. Here is a single layer of perovskites, and you have in the layer you have your perovskites. In this case, I was using lead. Would be this blue. Chlorine would be that orange. And in this model, they were using methyl ammonium instead of a simple halide. But this group right here would be the cesium. So what this is, and I wasn't able to get bonds to show on this one without connecting it to the organic ligands. But if you look at it, this brown colored atom is the lead, the greens are the chlorines, and the pink colored is the cesium. And it makes that same shape that we see in that last one, or that last model.
Last chance for quick question.
Yeah.
It's kind of related to the first question from Mary. Can you, what's the origin? Can you go to your orbitals for the structure A and B?
Structure B?
Well, to compare orbit, because you show this is the same structure but homoluma, right?
Yes, the blue is homo, the red is lumo.
And this is for which structure these orbitals corresponds to your DOS?
That corresponds to
With
the
a smaller
DOS
one.
that was on the left.
With a larger band gap, right?
Yeah, the larger band gap.
Okay.
It corresponds to the B.
So the larger band gap having homoluma orbitals, and again show everyone where the orbitals located. Okay, so they are on this intermediate, connecting inorganic molecules or atoms actually, right? Between the unit cells.
The layer, the iodine and cesium layer.
Now go to the case A for the DOS. Okay, and here's your homoluma, and they do not really sit on this kind of...
No, they're only in the perovskite here.
So probably this is the reason, right? So that you have this organic contribution of organic molecules, right?
Yeah.
Because this is three-dimensional structure.
This is a two-dimensional Yeah, this is a three-dimensional structure.
Three-dimensional, three-dimensional. Is it like we have top and
Like
bottom,
a
or it's in a periodic?
Thin film has two-dimensional features, but it is represented.
But anyway, so here the surface is completely isolated by these ligands, right? And
Yeah.
they do not contribute to your HOMO-LUMA gap, while the other ones have these orbitals of top and bottom completely occupied, and this probably caused this difference in the band gap, right?
So organic layer works as insulator, and inorganic does not.
Yeah. Okay.
Let's thank David once again.